Hi, everybody. I'm Michael Lane. I'm president of LiftPort Group, and we're glad that you are here this evening. Our team kind of stretches across a bunch of different time zones. I'll introduce them in a moment. If you are new to this, we host a monthly show, a monthly podcast to talk to our fans, our community, our stakeholders, to tell them what we're up to, why we're doing it, what the changes have been since last month. We try to be kind of rapid fire. We try to do a lot of things quickly because, there's a pretty good sized team. There's 6 of us. One of us isn't here tonight. And we go through a lot of stuff very quickly. So hang on. If you got questions, toss it into the chat. It's not a very interactive show, but we'll try to respond if we're able to. And that said, we're going to do introductions now. I'm Michael Lane. I'm the president of LiftPort Group. I've been involved with space elevator research for, hard to believe, 25 years. The first version of LiftPort came online between 2001, 2, and 3. It came online between 2003, 4, 5, 6, and 7. We primarily focused on nanotech and materials and also the mechanical processes of climbing. This is a new company. LiftPort is officially a new company, even though we've got a multi-decade legacy. We're starting from scratch. So glad you're here. Sean, over to you, please.
Yeah, my name is Sean Key, and I am head of LiftPort's Better Futures division or company. We're a subsidiary of LiftPort. We are a multimedia company that focuses on the commercial space in the intersection of money and mostly about space, anything tech, space tech. We have over 600 hours of videos in our library, and right now we also started our Better Futures Dispatch, which went over a year of publishing, and has right now we're right at 500 subscribers. So that's an excellent plus, and we are planning a lot of great new products, new avenues of getting information out there to you.
Cool, thanks. Joseph Lauren.
Hi, I'm Joseph Lauren. I'm an engineering intern. I've been here for about 2 months. Some of my responsibilities are taking, for example, a current simulation and adding onto it to allow us to really see what is going on our engineering side, see what we need to improve, and really help mitigate any risk when we eventually do send the elevator into space.
Cool. What year are you in and what school?
I'm going to PSU, Penn State, and I am going into my 4th year.
Nice. Jonathan Connell?
Hi, Jonathan Connell. I got 40-something years in engineering, and I'm doing the engineering stuff around here, the simulations and the design and some mission planning. And I'm located in Seattle. Very excited to be here.
Cool. Joe Luttrell.
All right. Hi, everybody. I'm Joe Luttrell. I'm the founder of Cube. We do a lot of research and development and satellite builds. Right now, we're working on 2 different satellite designs. One is an Earth observation type, and the other one is for running experiments in space. That's how we're working with LiftPort, is we're actually building a satellite to carry their experiment and test materials on orbit.
Terrific. Okay, cool. Let's just jump straight in. The hot seat first goes to John Connell, landing on the moon.
Okay, landing on the moon. So the moon is a dusty place. So let's think about that for a while. And particularly when we think in terms of the cadence of landings that will be needed to get to where we think we need to be. There are people with large-scale projects. Everything initially will need to be brought in, which will involve multiple large spacecraft landings per day, probably, if it pans out to what they think it will be. What's that going to look like? We've all seen the renderings where there's a landing pad that the rocket lands on, but what does it actually look like? We saw the launch pad at SpaceX after the first launch, and it wasn't there anymore. So these things knock a big hole. So we hope to fill that gap using our product, which causes no backblast at all. Now, the thing about the moon, the lunar dust, or the lunar regolith, the bit that's between the small rocks, is actually glass. It's made of glass, and it's extremely abrasive. It would make a great sandpaper or an air blaster for your car. And if you set it in motion, it's particularly dangerous. If you inhale it, it will turn your lungs into a bucket of blood. But it will erode things. So when Apollo, I forget which Apollo it was one of the last ones, landed on the moon. They landed next to the, forget what it was, Mariner 3, I think it was, Mariner 3 spacecraft. They landed 600 feet away from it. Now, the landing motors on the Apollo landing capsule were not as large as the kind of thing we're talking about today, especially for a Starship. But it sandblasted that previous landing 600 feet away from it and did quite a bit of damage to it, knocked pipes off it, removed the paint, polished the surface of the metal. But they observed all of the landings from the orbiting craft. And it turns out that when you land just the lunar module, you get some of the particles reach escape velocity and actually go into orbit. And some of them will travel thousands of miles before they stop moving. So this is a problem. And with large motors in a high cadence, what's going to happen? What's that going to look like? So Christian Savage has a plan for a large-scale lunar habitation, a good plan. And what she's doing is building berms around the landing sites, which it's the kind of thing you do if you want to hide a house or save energy, or if you think you've got a flood coming up the front yard, you'll build a berm in front of the house. So couple of things. No one's ever built a berm on the moon, and there's a big debate about stacking up soil. We intuitively know how to make a sandcastle on Earth. We don't know how to do that on the moon, and the change in weight is a big problem, we think, and to how things stack and what you can actually do when you stack things. So berms may work, but they're almost certainly going to be blown out of the way, and how close do you put them? And one of the issues that comes up is how far away from the habitation point are these landings going to have to be? Now, we know that the sandblasting goes hundreds of feet. It probably goes tens of miles too. So how are you going to get from the landing point and logistics into where the people are? Implies roads, railways, tunnels. I'm not sure. Again, LiftPort, we treat the moon with tender loving care. We come down softly, and there is no disturbance, and you can do as many landings a day as you want on the moon with no dust and no fuel either. So dust is a problem too. So we know that there'll be people walking around in suits, and if you're blowing up fine dust and spreading it around, the contamination will be worse than it otherwise would be. It'll get on people's suits, which means you have to have decontamination on the way in. You'll probably have to have multiple clean zones. NASA uses nitrogen baths. You walk through a nitrogen bath shower to blast the dust off you, and then you go to a second level clean room, and then you go to a third level clean room. It'll be very restrictive. So less dust, better. If you've only got it on your shoes and somewhere where you fell over, it's a lot easier to clean up. But I think the real danger here is just remembering what Starship did to the launch pad in Texas. That is going to happen potentially with every landing on the moon. I mean, more so because it's not more
so. There's no atmosphere to dampen it. Yeah.
So we offer a prime service solution for that. And certainly there are engineering fixes for this. There's a guy I've seen on LinkedIn who's got a mat that he lays out. It's a mat, so it's going to have mass and cost and issues, and you have to peg that mat down. And most materials will melt or burn. And the materials that don't melt or burn, it's still going to fuse the surface of the moon underneath. There's also laser sinter the whole surface, but that's very expensive and time consuming. So it's not been worked out, but it's not a problem that LiftPort has, and it's not a problem that LiftPort will ever have. So I think we fixed it.
All right, we're going to switch over to Sean. Going to talk about better features and first principles.
Okay, so lately I've been writing about orbital data centers because that's an easy fruit. And I actually came to the conclusion that we're going to see something of that nature. And I wrote about it. And I got a response back. People saying like, hey, you don't know the physics. People trying to teach you the physics and stuff like that. And well, being the red-blooded person I am, going back to my blue-collar days, I wanted to swing, but I decided let's dig it. Let's see if I'm really right. And so I started digging into, engineers call the first principle. You work on the first principle. Steve Jobs was known to focus on first principle, on problem solving. And Elon Musk obviously focuses on first principles. So what is the first principle? And that's where you can discern and get down to what you can prove is true. And that way you can cleave away your assumptions and have two different categories. And you start from what is true. So let's take the orbital data centers problem. All right. And this is not going to be an essay about orbital data centers. It's just an example. All right. So orbital data centers, people get the image of a Connex box in space. And of course, people are going to say that doesn't work. And they're right. They're right. But saying the physics says so, or the physics says orbital data centers cannot exist in space is wrong. Or physics says this is your constraints that you have to work with. The engineers can work on what are the solutions could be for those constraints. And then we have to figure out what the economics would support that. But physics does not stop it from being. Once you figure out what the engineers figure out what the solutions are, then we can figure out what the economic impact could be, where it would need to be. And a lot of that I already knew, but what made me come down and say we were going to have something is I had an understanding of agents from a personal experience working with LiftPort with agents. So an AI agent, one person can create an AI agent. One person can create multiple AI agents. These agents run 24/7 without supervision. Ideally, you come back and check on them regularly, make sure they're not doing something running amok, but they can run by themselves. One person can run 100 and manage 100 agents. That's an exponential impact. And I do not know an organization on this planet, if they can financially prove that it's cheaper to run agents than human labor, they're going to convert to it. So IT has an incentive to meet that demand, but there's not enough data centers on this planet. And by the time they can get enough, you can get past all the regulations, all the problems you have with trying to put them in because nobody wants them in their backyard. You're going to need every spot you can get. And plus, on top of that, space is going to have some sort of orbital data capacity. So we're going to have to solve that problem regardless. And we're probably going to see, and it's going to be at a large scale. There's certain things that's not going to happen, though, because you cannot solve latency. That is one of the physical constraints you cannot engineer around, because we have certain things on Earth that we have to do at speed, like business transactions, military operations. They need instantaneous transmission for a lot of those operations. But in space, you can take up some of the slack. So that's the reason why I posted that. But what it really showed to me is the importance of understanding the first principle. And then going back to it, you're drilling down to where that fundamental truth is that you cannot deviate from. And you cleave all the assumptions away. The assumption is what you're going to work with and solve. But that fundamental truth is what you know, and you work from there. And you work your way backwards. So instead of saying, orbital data centers just can't go in space, we didn't look at the architecture or the artifact. We looked at the function. So after this, my next time around, I'm going to show how we do it here in LiftPort.
Right on. Joseph, go ahead, sir. You've got 5 minutes on simulation extension.
Yeah. So I was originally given a small simulation to try and improve our system that we are creating here, our Lunar Space Elevator. It was small, but it was the bones that really needed to be started. It was an HTML file. So if you really wanted to get down and into it and you wanted to add all the mathematical pieces that you needed to really try and understand what is going on when we do eventually launch this thing into space, you need to change that to Python or something else, because HTML is just very, very basic for creating complicated math. So something I did was I split our simulator into an HTML front end and took the back end and made it a Python code, and I added things into it like variable gravity. I extended it easily 100 times the length that it currently was. Um, and I also tethered it at different points so we could see what was going on. I gave it different safety factors for different pieces so we could see what was going on at each individual point, see if one tethered end was stronger than the other, what we could really do for LiftPort to figure out, okay, here are our issues with our current thoughts. How do we fix this? What do we do? Are we missing anything? And that's something that I've really enjoyed doing here. Is not only have I been able to work on it individually, I've gotten help from John, and AI systems have been a really good friend in creating solutions extending, for extending code. I myself am not a computer engineer, so this is something that having these AI systems that we've partnered with, like Liam and Bike for Mind, they have been really good for us to allow us to extend these simulations and codes. Another thing that I've also worked on is adding in figuring out where along the line the issue is. So you can have a safety factor, and if it's 100,000 kilometer strip of material, let's just say, anywhere along that line, the safety factor could be, for example, 0.5. You don't know where that's going to be. So, really being able to pinpoint where all that stress is coming from is going to be very key, because if it's close to somewhere where the gravity is very low, then you know the issue is over there. Whereas if you're close to somewhere where the gravity is higher, making higher weight as stuff moves along, that is going to be very important, at least from an engineering side. And something Sean said is these are constraints we have to work around. It's not impossible, but they are constraints. And that's why we are doing this simulation stuff, because if you don't, things are going to break when you get there. Things are just going to break. That's why companies use FEA and a bunch of other systems. But yeah, so as I said, these systems are really important for us as a company to make sure that what we are doing is not only mathematically backed, but it also makes sense from an economic standpoint when we get up there. So if we have an issue, we need to be able to work around it and the constraints around it. In my next thing, I will be talking about my individual project and how that's really going to be important in what goes into this simulation, and how we are going to be working around other constraints that we had not thought about previously, but now we believe that we have everything nailed down.
Awesome. Thanks a lot, Joseph. I'm going to take the next one. Dallas, 100% saw your pushback there. I'll for those that are kind of watching afterwards. This is from Dallas. I totally disagree with the conclusion that what happened on Starship Launchpad will happen on the moon. 2 different vehicles with totally different numbers of engines. Not all 6 will be firing upon landing. I understand that, and this is definitely an apples to oranges comparison. Yeah, you won't have that many engines running all the time, and certainly not with that much thrust. But the difference is that they did that at Texas at sea level, and they had the whole weight of the atmosphere, 16 pounds per inch, on top of them, and you won't have that on the moon. So there's no buffer. There's nothing to push back against. So yes, it won't be as big a rockets, but also you don't have the friendly atmosphere to dampen things. So we simply don't know. And I think it's premature to say that we do know those answers yet. All right. I'm going to swap gears for a second and talk about stuff that is a little dull. Sorry about that. So this popped up yesterday, and it is not showing. Yeah, there it is. Okay. The Space Foundation issues a report every year. It is a retrospective of the year before. So this is, even though we're halfway through 2026 already, this is entirely 2025 data. It's important to really understand what the global economy looks like, because that's where we're going with all of this elevator stuff. And we talk about the cisLunar econosphere and building it out. In order to chart the course remotely correctly, you need to know what the numbers look like. So we just surpassed a $686 billion industry. To put that in perspective, the very most valuable company in the world is Amazon, with $700 billion in revenue last year. So we are the size combined globally, commercial and government sectors combined, to be a little less than Amazon. Personally, I'm pretty excited about that, because you could honestly say that Amazon started about the same time as the commercial space sector did. And my hunch is that we are going to surpass that. So I'm pretty excited about that number. I'll post the link to it in the chat here in a moment. But some of the things that I take away from this thing, I disagree with some of their analysis. And Sean's friend, Dr. Dan Gerritsen, is pretty famous for saying, look, only a third of this space economy that keeps getting posted about is actually happening in space. And this document actually says it pretty clearly. It says that most of the space economy isn't in space, it's in your pocket, because they're talking about timing and transactions and position navigation and timing. There's one group, I don't think it's this one, but there's one group that counts Uber as a space commercialization tool. Obviously, I don't think that's accurate, but Uber couldn't exist without the PNT component. Satellite manufacturing is way up, 62% more than the year before. Almost 4,500 satellites were launched last year. Starlink itself has 10,000 satellites, and there's another 6,000 out there on top of that. One little thing that kind of almost didn't make the news is $364 million of the quote lunar economy. Now, as far as I was aware, there wasn't a lunar economy. So I was a little bit surprised by that. So it's a report worth reading. It's a report worth investigating. But I'm taking that lunar economy piece with a little grain of salt. They're focusing on Firefly and things like that, but I'm a little skeptical of their numbers there. All right, and with that, we're gonna swap over to Joe Luttrell.
All right. Well, thanks everyone. Thanks, Michael. The first thing I want to discuss tonight is a little bit about the laser development we've been working on. For those who don't know, satellites up to this point for ground to earth and earth to ground communications have used radio. The problem with radio is that frequencies are a finite resource, and we're running out of frequencies that we can use even for satellite bands. And this is a compounding problem. The more satellites we launch, the more ground stations we need, the more radio frequencies we need. It just becomes a bottleneck. So much so that right now, getting paperwork through the FCC is an incredibly long process. So why not just skip the process completely and minimize the radio and move to light? Laser communication's a known thing. We've been using lasers inside fiber optics for decades. I remember when the first fiber optic lines came on for phone communication. It was like, wow, this is amazing. Well, now we figured out how to do lasers in free space where we can accomplish the same thing. Now, in order to do this, you need to have some precision pointing, and you need to have a powerful enough laser and also a powerful enough receiver. So our objective with this particular mission is commands will be sent up using a standard radio, but all the data we gather will be coming down via laser. That just saves us that step in the licensing process. But in order to do that, we had to build it. So I'm going to try and demo this. Understand this is a benchtop set. It is not designed to fly to space. It's to show how it works. And in order to show how it works, we had to make a couple of changes. One, the pan tilt system that you're going to see will move very quickly. That's not how it works in the real world. We've actually sped it up nearly 50 times in order for you to be able to see it. It is a very slow moving object. The other problem is the laser happens so fast that we've had to slow it down so you can actually see it working. This is using a TCP/IP protocol. So this will talk to the internet directly. You can take all of the bits that we're sending via the laser, and it will translate straight into an internet protocol. So it's pretty slick. This is a first time. I'm going to pick the camera up. We're going to go and look at the rig, and then I'm going to put the camera back when we're done. So here goes nothing, everybody. This is probably going to not work, but we'll give it a try. Okay, so here we go. One camera being lifted up. All right. So here is our rig. This is the pan tilt mechanism here. It's not very large, as you can see. The laser we're dealing with is a 0.5 milliwatt. We don't want to be doing anything larger in the lab. For space, we will be using a 5-watt laser to make this work. So it's pretty powerful stuff. Okay, everything back this way is the controls. This is the laser. What I'm going to do is I'm going to start it up. It will go through a pan tilt test cycle, and then I'll set a card up and you can see the laser actually pulsing out all of the information. That is, if I can keep everything in the camera frame, because it's mirror imaging and I didn't realize that. Sorry, folks. Okay, here we go. Let's move this little pan tilt unit.
It looks like our PD2.
It does. And now the laser is engaging, and I don't know if you can see that.
Yep, we got that. Thank you. Yep.
Whoops. There we go. So that is running at basically 10,000 times slower than what we would be doing in space. So that's just
Brilliant.
a quick demo of what we're working on right now, and hopefully we'll have a couple other demos a little later on.
Can I ask
Alrighty.
a question?
Yeah, go ahead.
What does the receiving system look like? Do you have plans? Are they standard parts?
Everything is pretty much off the shelf, and off the shelf, but
Ish.
highly modified.
Right.
And I'll be showing that a little later.
Okay, good.
All right.
Good.
Cool. Great. All right. I'm going to take another 5 minutes myself to kind of talk about what this last week has looked like. I did something that I don't typically do, which is go to a pitch competition. I think nobody who's listening or watching is going to be surprised to say that I'm to hear me say that I'm not particularly skilled at this. It's not something that I've ever really had to do, so it's a new tool I have to learn how to use. It was quite interesting, and one of the big takeaways was, maybe I'm in the wrong room. So this was it was a defense-focused program for Friday, Saturday, and Sunday. It's called a scale-a-thon, so it's different from a hackathon, but it's the idea that you come in with a relatively blank slate and decide you want to build a business. Now, there weren't very many people there, and and everybody was already working on their own things, so that was a little bit strange, a little bit chaotic. But one of the things that has really struck home to me several times is that maybe this isn't the right room for me to be in the first place. That if you're a software as a service style company and you've got yet another digital app, it's pretty easy for an angel investor to say, okay, if I put 200,000 in, I'll get 500,000 out, or if I put 500,000 in, I'll get 5 million out. Or if you're the early days of Facebook, it's 5 billion out. Those kinds of systems are very easy for investors to understand, and therefore it's easy for them to write checks. Our project is not like that, and it is very hard for people to understand what it is that we're doing and why their quote unquote small check of $200,000 moves the needle at all. If your project is a $350 million project, how many people do you need at 50 or 100 or 1,000 or $100,000 to make that number work? So it was a little humbling. And it wasn't really a surprise because I've been wondering about that for most of a year that I've been in this environment. Contrast that to a different environment that I also was in Monday, where we're starting to talk to people that could potentially become clients of ours. Transportation clients for LiftPort's space elevator, transportation clients, storage clients for our Lagrange Point station, LiftPort station. I've had 2 different conversations, Monday and another one on Tuesday, with folks that are starting to be interested in using our system. And I'll tell you, it's night and day having conversations with folks like that versus folks like the traditional angel investors. And what we're finding is that the people that want to use our system are the most likely to invest in our program. So that's been kind of a big change. What I said on Saturday or Sunday at that scale-a-thon was, I think I'm in the wrong room, but I don't know what room I'm supposed to be in. And then coincidentally, Monday and then Tuesday, back-to-back meetings with potential clients, we're beginning to talk to them as investor clients, people that will use our system and invest in what we're doing. So that's new. It's very new. It's not really a plan yet, but it is an epiphany. So with that, I'm going to switch it back to, it is John's turn. Requirements. John Connell.
Okay. So I've worked in a lot of different industries, and I'm a cross-discipline guy. And most of the companies I work for have been small business. That's defined as under $200 million. And you work in an environment where you've got to get stuff done quickly with almost no budget. And if you fail to succeed, you've lost your job. And I've spent like 35 years in that environment. Arriving in aerospace, I see something that's a little bit different. And aerospace prides itself in saying, oh, startups are scrappy. But when you actually get in that environment and you look at what's going on, people leverage their own experience. That's all we can do in when they make decisions. So I was working in a company where we were welding stuff together, and we had a few weeks to get something done, and it had to be put together and tested, and then we moved to the next stage. And a lot of the engineers in that company were concerned we weren't following a procedure, concerned we weren't doing quality control, concerned we didn't have X-ray machines. And those are all the correct things to be concerned about, but not when you're building a first prototype. So you have to understand where you are in the great scheme of things from project inception to the end, and you adjust what you expect to do to a project according to where you are. And if you're in a little company with 3 staff and no money, you can't be expected to perform NASA quality control inspections or work to AS 9100. It's not going to happen, and it's silly if you try to do it, and it will only slow you down. There are times when you have to do that, like flight is a case where you do that, but there are times when you don't. So the most important thing I find when I'm hiring people that have worked for successful aerospace companies is to get them to understand that they know how to do it perfectly, and we want it done perfectly too, but there will be times at the beginning of a project when it won't be done perfectly because it shouldn't be done perfectly. You should leave holes in procedures. You should rush things. You should wave your hands a few times. That's okay, and that's how you move on quickly. That's scrappy engineering, and that's how startups flourish. And it can be a limit. So aerospace does things really well. They are great at quality control, doing difficult projects, but they're really bad at stepping back from that and doing things in a little bit of a scrappy way. They're not good at that at all. So let's talk about product development stuff. There's waterfall project development, there's agile product development, scrums. There's a lot of talk about which is the best one. And the truth is, and I've worked in them all, they're all crap and they're all wonderful. And you shouldn't actually believe one is better over the other. Agile is great for software. I don't think it works at all for hardware. In most of the aerospace clients, startups I've been in, there is no client. So any development system that needs you to refer to the client, you can't, because you are the client. So a lot of those systems break down. And then the message with product development is you need to come up with an entirely new system based on all the other ones, which you know about, to develop your product in that company. And the system you use for the first prototype will be different to the first flight, obviously. And you need to modify those systems. But if you rigorously apply one set of standards that you never get anywhere. And that's exactly the kind of thing that the Department of War is trying to get everyone to understand in the country. You've got to know when to do a lot and know when to do a little, and know what the difference is. So SpaceX are famous for having no managers. And I worked in a company recently that also had no managers, and it was not a good experience. And I think it's offensive to managers too. Managers, it's a nasty sounding word, but they're leaders. They're sources of inspiration, and they're sources of control and reflection too. So managers are really important. And just think for a second, one of America's crowning achievements, which was the D-Day landings. How would that have gone with no managers on the beaches? You take out the sergeants and the captains, how would D-Day have gone? Now, these are well-motivated troops that have been trained, absolutely. But what would have happened with no sergeants and captains? And that's the thing. You've got to have people that monitor things. Personally, I would love a team that's under the age of 35 to give me all the suggestions of work. They're going to be better than me. They're going to have fresher minds, and they haven't learned what you can't do yet. But on the other hand, you do need an experienced guy looking down on that, taking those great ideas. That guy knows what you can't do and what you shouldn't do. And that's the filter, and that's what a manager is. That's that filter. Motivates the team and helps those people to be successful. So really, that's my message. That
Right. I'm gonna shift it over to Joseph. Go ahead, Joseph. You have 4 minutes to catch up.
Yeah, no worries. So I'm gonna go pretty much in a very similar route that I was last time, where I was talking about how we were expanding on the simulation and personal thing that I need to do. It's actually my individual project for my internship here, is creating a more circle safety factor extension that's going to be basically like a plugin, not only for this simulator, but any other simulator. Sean, do you have the photos I sent you?
Yeah, hold on.
For anyone who doesn't know what Moore circle is, basically, imagine you have a solid material, or even, as you'll see in the photo, a hollow material, and you twist it. That angle of twist is going to change the stress, the strain, and the principal stresses all on the system. So that is going to also then change your safety factor and how that material really reacts with the environment around it. It's very important for combined loading problems, which is something that we are dealing with. We're not only dealing with the combined loading problem, we have a lot of other things going on as well. But yeah, so what you'll see here is that each angle has a corresponding stress and strain with it on the axis that it gets twisted upon. You will also see that the angle is multiplied by 2 because Moore's circle is double what the actual angle is. So this is very theoretical to get out a real answer. If you move on over to the other photo.
Right. It takes me a moment to set it up.
Yeah, no worries.
While he's doing that, talk about your individual project, what you're doing in terms of time, and the clock is ticking, and you only have 1 minute, so go fast.
So I had a week or two now. I've been sick for the last week, so it's been a little hard, but I have all my other responsibilities on top of my current new responsibility of getting this individual project done to help and further LiftPort's and our goal of getting the elevator into space. You will see that everything, depending on if it is hollow or solid or anything else, changes just exactly how this combined loading problems and angles of twists work, which is the real issue. And that is why this needs to be an extension plugin instead of just being put straight into it. If it was put straight into it, it would rely solely on the dimensions given, and it would have no room for flexibility.
Awesome. Thank you very much, sir. All right. I'm gonna take the next one, and then Sean, you're up next. There's some stuff that we've been doing on our website. Let me do a quick screen share. Nope, wrong one. So, done some pretty big overhauls to our website. I always point out the clock, 804 days to go. Tick, 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 tick. It's spooky because we've burned 20% of our days, and we're still deep in the weeds of development. So that is, honestly, it's a little frightening and kind of makes me crazy. But there's some pretty good stuff in our website. You can take a look at it for yourself. What I've been working on recently is trying to put together a report section so people have a good idea about where we are, right? So we're doing quarterly reports, telling our story, what we're up to. And these are pretty detailed. These are north of 80 pages, pretty close to 80 pages. Report number 3 is in progress. I did not get it loaded today, which is a little frustrating, but I'll get to it soon, probably this weekend. We've also got a ton of appendices. These are quite useful. You'll notice that some of them get superseded as we get more current information. So this document, this page is kind of reverse concurrency. So you know the stuff that's at the top is most likely to be the most useful. And then the last piece is, I just got this posted today, is our podcast schedule and our shows. So it's happening, starting to get this stuff out there for the public to kind of help tell our story better. I think anybody who knows me knows that I believe in transparency. And this is one of kind of LiftPort's core values about telling our story and getting it out there. So our back corporate reefs, this is the 4th one. And so that's all up here. And there's going to be a bunch more appendices. I probably have 20 more appendices that are sitting on my hard drive that need to get posted. So that'll be kind of a core task over the weekend. Yeah. So with that, there's not much more to say about the website. So I'm just going to give the time back to Sean. Sean, go ahead and come on board, please.
All right, we'll pick back up where I left off on the my last segment, and this is actually how we use first principles in LiftPort. Engineers can tell you how they use it, and I know they use it all the time. It's not something that's commonly talked about outside of the engineering sector. Some business people might talk about it, but it's not common. So, but what we do here, we do spend a lot of time focusing on deciphering what an assumption is and what we do know as facts. And we go from there. And to get to that point, when an organization comes online, you first start off with, how's that company going to orientate to this problem? Some companies actually start off with the first principle and build the company around the first principle. How do you solve a particular problem? So in a sense, let's take what we are actually doing. We're trying to solve an infrastructure problem in the cisLunar system. We're trying to make sure we make an economically efficient way to get down to the surface and back up, continuously bringing product and driving down the cost and making it safer and more consistent. So that's what we're doing. That's the function of it. But we also had an idea that was plausible. So we're starting with the assumption and not the first principle. Other organizations will do it reverse, and there's nothing wrong with that. Whatever works for you. What we had an idea of a technology that could work because it proved that theoretically it can work with existing tech today. This is not something we have to invent. We just have to solve the problems. Okay, so we started from that premise, and then we go from there. Let me pull up and find my image. Give me a second here. Trying to do all these things at once is it's a little time consuming. But hold on, and if I can't find my image quickly, I will just drop it and move on. Because there it is, downloads, and for whatever reason, my image is missing. Okay, well, we'll just have to worry about that later. All right. Anyway, so what we're doing here, as once you got your orientation figured out, then you start tackling the problems that come up, and then you start using the first principles, and you ask, what do we know is true? So going back to the science, we know the science is our constraints. Everybody knows that. And then the engineers will sit down and they'll figure out, what do we know that can work? What do we know that we don't know? I mean, there's three paths of knowledge that we have. We have the known knowns, the known unknowns, and then of course there's those wild cards that we have no clue that exist. They'll come on and throw a monkey wrench in you, whatever it is that you think you do. You know, they'll humble you, a little bit of humble pie.
Yeah.
So we got that to work with, and then sorry about this, folks. I'm just getting back on track, and we'll get asking those questions: physics allowed? What are the constraints? Can material science support it? Can engineering build it? And do the economics work? Is there a significant enough long-term market demand? And some of those are, as we're building these along, we're starting to figure out, all right, this is what we know. So we know the physics don't say no. We know that the technology exists to actually build it. We just don't know how we're going to put the secret sauce together completely, but we're working on that. And then the economics, we are also discovering that we're working on, but it does have an significant economic impact once it gets deployed. So let me go on here. But all this also requires in-depth research, in-depth intelligence gathering. We have a lot of data we have to collect. We have a lot of data we have to go through. This is the reason why a digital twin is absolutely important for this project. Because if you can't prove it digitally to go to the next step, you're going to waste a lot of money. You're going to blow through a lot of capital. This is why this is important. And this also helps you discern what assumptions are surviving to the next step as well. And that's when you move into the next phase of when you figure out, all right, we're going to do the physical parts now. We're going to test these assumptions out. So those are essentially what you do when you use first principles.
I'm going to toss in there for a second and just kind of describe the digital first component a little bit more. We've had some pushback where folks want us to start getting their hands dirty and start building stuff. And I get why they would want to do that, because that kind of talks to what Connell was saying earlier, that there's kind of a certain way to do things in this industry. But if we are constrained by capital, which I have always believed that we were, the lowest cost way to partly solve our engineering problems is to build it as a digital twin. So just not trying to take up your time there, Sean.
You're fine. You're fine.
Yeah.
And yes, and that is a very key component there, because we don't have time is not necessarily on our side, because we're not the only ones that think we can do this. but we're the best ones at it because we have the most experience. You know, Michael's John's a talented engineer. I've actually worked on with Michael in the previous LiftPort incarnation back when it was a terrestrial company. So I have an understanding of the elevator, not on the technical side, but on the business side and on the economic side and the financial side. And even when I looked at the numbers and what Michael was projected that we could do it in, I cried a little bit, but I said I think I could figure it out.
That's
I got an opinion about that. Simulations are great when there's a justifiable reason for them. So we're simulating the elevator right now, or the ribbon that holds it all together, because we have to. We can't go up in space and pull a length of it, although we are with Joe presently. The only way we can look at it in bulk is creating a simulation. And it can't be done with the usual FEA and CFD tools, happily, because they're really expensive and we don't have the money for them. But we're planning our own way to simulate it. And that's a great use of digital twins. And to do that, you go back to first principles. As Sean said, we started at the beginning and slowly made a more and more complex model. And got good results out of it. What I don't like to see in aerospace is when you ask somebody to make a bracket that big and they won't draw it, they'll go straight to simulation to test it. And that's reliance on it, and that's plain dumb, in my opinion.
Just walk over to the machine shop.
Yeah.
All right. Joe Luttrell, you got 4 minutes, sir.
Okay. Well, I want to first acknowledge Jason had a question about what our bandwidth was. And for the laser, we're testing at 1 megabit per second, but ultimately we can get to 1 gigabit per second using this technology. That's 10 times slower than what SpaceX uses on their systems, just to give you an idea of how powerful the lasers are for a Starlink versus what we're doing. But hey, one megabit per second is a win. Anything above that is gravy. So just start there. All right. Well, we've talked a little bit about the satellite side of things. And my computer is having fits. All right. Let's see if we can be careful here. All right. So I'm just going to spin my camera around here because if you're going to go to and build a ground station, you need a way of building a ground station. This is a standard Celestron 11-inch telescope. It's exactly the same one that MIT used when they built their prototype ground station for laser communications. We are not treading new ground here. This has already been done. One of the questions initially was, can you actually move this thing fast enough to make it work? And yeah, the answer generally is yes, you can. And of course, that one didn't work, but I was hoping to do a manual, but I have it all in the computer, so that's probably what's happening. So let me shift over here real quick to the computer. And you can see that we have, we're using gPredict there. So we have all the ground track. We can track satellites with this already. We've been testing it. And so tracking ours is going to be essentially a no-brainer, especially with some of the optical tools we're using. Again, the protocol here is the same as what we're using, TCP/IP based. And the neat thing about the laser is that the spot that it hits on the ground is greater than 10 meters across. That's how much deflection there is in the laser from 450 kilometers up. So we've got a 10-meter circle. If there are questions about the power that we're using or receiving from it, you can combine telescopes. So we can put a cluster of 6 of these on the ground, all working in sync, and then combine the signal back, and that's how we can improve the accuracy and the data stream. So there's a lot of cool techniques that can be done, and they're fairly, for aerospace, they are fairly inexpensive.
It's fairly hard to intercept that too. If it's 10 feet across, you'd have to be standing next to the actual antenna to break into it.
Exactly. So it's secure communication. Now we have put security on our protocol already, just to be on the safe side. Even though it's TCP/IP, it's a form that was submitted and rejected because it modified it so that the TCP/IP packets themselves were pre-encrypted.
Mm-hmm.
Tim Berners-Lee came up with it. The guy knows what he's doing. The W3C Foundation didn't accept it, but that's what we're going to use.
Nice.
All right. I'm going to take over the mic again and showcase this document. We don't usually have back-to-back important documents that get released essentially, one day after the other. But that's what happened. That's what happened today. The director of the Science and Technology Policy at the White House, Dr. Michael Kratsios, pretty well respected on both sides of the blue versus the red aisle, came out with a new document that basically says we're rebuilding the science infrastructure of the nation. It is pretty interesting, some of the things that they say. There are a lot of talk about space specifically. There's a whole section on, where did you go? Sorry, I thought I was sharing this screen on. I am pulling this from my hard drive. Can somebody on my team go and find this document at the White House? I'm sharing my PDF off my hard drive instead of the actual site. So this document, in their own words, is an Apollo-style mission plus an AI multiplier, from discovery to the factory floor. Of course, it's going to say all inside America's borders. But there's a lot of stuff in here that really focuses on space. There are 6 big themes here. AI, of course, that's kind of driving everything. Quantum, fusion, space, robotics, and semiconductors. I'm going to say that again. AI, quantum, fusion, space, robotics, and semiconductors. That is what this whole document, 123 pages, is focused on. And it is, I think it's a game changer. Credit where it's due. I think there's a lot here. They pulled a bunch of quotes from the early DARPA days. They pulled a bunch of stuff here from the original X Prize Foundation and the idea of using prizes as a catalyst. It's all about the private sector. How do we use America's national laboratories and partner with the private sector? So to that end, there was a lot of changes and upgrades in the SBIR language that came out just a few weeks ago. And that's a goal to link the private industry with the nation's laboratories, both the national labs and private universities. It's pretty interesting, this document. I was expecting it to be very fluffy, but in fact, it's got a lot of depth to it. They've got the national budget in here and a priority for research and development. It's a pretty meaty document. I had low expectations, and I was honestly quite surprised by it. I felt a little bit like there was a tiny bit of throwing industry under a bus in here, as if we haven't already been doing the work. So that was a little bit surprising. I didn't take it personally. I thought that perspective was a little strange. Um, as a White House document, of course, it definitely has a certain flavor in the language. There's a reason it's called the Golden Age, because everything this White House touches is gold. But the document is powerful, and I think it is going to lead to some good things. So with that, I'm going to stop sharing it. I recommend that you go take a look at it. Jason, thanks for finding it, buddy. I appreciate that. That is the correct document. Sean, same thing. Thank you. So whose turn is it? Who hasn't gone? Joseph. Let's go with Joseph. Lauren.
Okay. So finishing off on why we're using a simulation at the start. I know, Michael, you touched on it, and John, you touched on it, how we do have a budget, and it's, maybe not that we can go build the whole thing right now. So we need to figure out a way to test this. And one of the big things we found was an issue with the safety factor because of a very, very specific problem. And John has a background in dealing with this problem, and he caught me up to speed. And so we thought about it, and we really sat down, and we were like, okay, what can we do about this certain problem? And I know Sean earlier said that engineers, they understand constraints and then they try to figure out what can be done, and that's precisely what we did here. So this simulation really allowed us to see some of the issues that we are having, and we have figured out how we are going to fix it. I can't necessarily say what it is right now, but we have a patent in process to get this patented, and we are working to make sure that this ends up fixing our safety factor problem. I truly believe that this system, is something to be proud of as an engineering group, because this is a problem that has never been tackled before in the history of, well, I guess the world,
Right.
history of everything, right? So I'm really proud of our team for being able to figure this out, and we're going to figure out how to implement this not only from an engineering standpoint, but Sean is going to help us figure out how to implement this from a financial standpoint, right? And Michael is going to supervise us and make sure that it makes sense.
I'm bringing the lawyers, right?
Yeah, right.
When all is said and done, at the end of the day, we got to be able to back this up and protect it.
Yeah. So this is something we've collectively worked on and thought of, and this is a collective group effort, not just from one person, but it's a collective effort on all of our parts. And like I said earlier, I couldn't be more proud of our group.
I'm super proud, for sure. Absolutely. Describe the problem a little bit more. What is it that where is the problem at? Like, what is the thing that you're trying to solve?
So the problem is actually attaching to the moon. That is a very big problem, that we have the weight of the material, just the material isn't able to support itself currently, and able to support all the motion going through it as we move stuff towards the moon. And so instead of giving up, we've decided, okay, we are going to look at different solutions for the two different issues that we had here. And we came up with solutions. And like I said, we're working on getting a patent for it.
Awesome. Okay. All right. Let's move to who's left. Just John Connell and Sean. Sean, you are still left. You go.
All right. So wrap up this conversation about the first principle. I was actually sitting there thinking that, in the context of what we talked about, engineering, economics stuff, this is actually used in strategy. And you go back to something that we use at LiftPort that was developed by Michael, and he showed it to me years ago, almost decade and a half ago, longer than that.
Yeah.
It was the media process. In that process, there's a technique called deconstruct, reconstruct. So the idea is that you sit down, and when you get ready to set up your enterprise, you'll look at the vision and values. And there's the first things you want to tackle is your vision. Where you think you're going? Where are you going to go? And then you're going to sit down and you brainstorm this. And you really try to brainstorm it in detail, as much detail as you can. But it has to be unique detail. And you just dig and dig and dig until it hurts. Until you get ticked off of each other and walk away, and we have to come back and do it again tomorrow. So then you sit down. Once you get a big pile of concepts, then you sit down and you look for redundancies. Does this really mean this here? Does this really mean this here? Can we say this with this? And you really strip away all the excess noise, and then you get what you get. You keep on doing it till you can't get down any further. You have the truth of your vision. You have the fundamental truths of your vision right there. And this is important. I mean, this part is very important. This is where you know what direction you're going and what it's going to look like. Then you go and you do it to your values. How am I going to behave and act doing this? And you do the same process. You put out there, what do you value as ethical? What are your values? And you lay it out there. And once you do that and you go through the same process and you say, well, does this mean this? Are these overlapping? Do I really need both of these sitting there when I'm really trying to say, I'm actually saying the same thing? Or can we just restructure this a little bit where it means both of those things? You keep on stripping away until you get your value system really locked in. And it is truthful. There's not a wasted word in there.
No.
Vision and the values. These are important, because these two things are what's going to help you develop your mission. That's where the value comes in. This is where it really helps you fine-tune your strategy. And all this really is first principle. What is the first principle of your vision? What's the first principle of your values? And then you come up with the mission. And once you got your mission down and you've done it all first principle, guess what? You're going to do this again when you start figuring out your policies, your objectives, your strategies, and your tactics. You're going to do it again. From there, you jump into goals, investment, and tasks. I mean, there's a whole list of things that goes in the process, but it really starts down that we're doing it from first principles at the very start. This is the reason why this is so important about the first principle. I think this is a business that should be more prominent out there. So for me, go ahead, Mike.
One of the things that we do, I've got the vision, mission, values. I've got our core philosophies up here, compass philosophies up here on the screen. One of the things that we do each quarter is really try to identify, like, what are the priorities that we have to deal with. And what we've done, this goes back to what Sean said a minute ago, is taking a look at our vision, mission, values, crunching them down to the smallest possible level, and then using those words, our vision, mission, value words, and assigning them a priority so that we can start working on stuff. And this is a thing that we work on quarterly, and it's our clarity. It's where we're going, why we're doing what we're doing. It's kind of core to who we are. So.
Yeah, it is part of the DNA in the company. And I think, and unfortunately, a little bit of, I can do a better part of promoting this. I think Michael could have done a better part promoting it too, tooting his own horn a little bit. But no, but the truth is that whatever system you use, you need to stay focused on the first principles. It saves you an immense amount of time because there's a lot of noise out there that you have to contend with. That's the reason why I stopped watching news, because it's really hyperbole and advocacy for assumptions. And I mean, half truths and partial truths to make your point doesn't do anybody any good. But the same is true. It's bad for business if you have to use partial truths, half truths, or laziness for accuracy. It just gets under my skin. But you don't really have to do that much. You just have to be a little bit more attentive and disciplined when you actually apply this, and consistent. Be consistently applying it. And so that's my takeaway from first principles, and that's my discussion. I usually don't like not having the last speaking part. I like to have the last word, but I have to go with the flow, guys.
All right. I'm gonna do. We got Joe Luttrell coming on for ground stations in a minute. Then John Connell and I are going to talk about some of the stuff that we put onto the website and Lagrange Point. And then we're going to kind of close this out and maybe open it up to a discussion. Before I want to do that, I'm just going to take a couple minutes to have a conversation with Jason from our audience. Jason, you spent 6 hours on the Golden Age document today. Is that what I'm understanding? I'd really like to know if that's what you meant, because that's what I'm looking at. And then I got to ask what and why, because I'm really curious. You probably know this document better than I do, so I'd be really interested in your take on that. Because I think it's a pretty big deal, but I did not spend 6 hours on it. So if that's what you did, I would really like to understand what your epiphanies, aha moments, frustrations were, because I would like to know what they are. All right. I'm not spending a lot of time paying attention to the clock for a second. I am going to take a moment to describe last month at our stakeholders meeting, this open invitation meeting. We talked an awful lot about the industrial infrastructure network, and we've done a lot on it in the last 3 weeks. We are ready to start bringing on clients. We have been doing some background testing, and we've got 4 clients in various stages of onboarding. That's less than I was hoping for. I was hoping to have 10, but turns out there's a problem with the onboarding, and I had to rebuild some really core pieces of that of that document. So not document of that website. So the industrial infrastructure network is ready. We are taking on clients, but it is very clunky and it's very time consuming to figure out this onboarding process. So just want to give everybody an update. My goal is still to get at least those 4 signed up and working this month and finish them out. And then I'm just going to push back and say, okay, we'll get 6 more in August to get us a total of 20. That's what I'm aiming for. I know that a lot of folks don't fully understand what we're doing with the industrial infrastructure network. Our team internally absolutely does. We all think it is core to the success of our business plan. It's one of the reasons why we had this epiphany about that investor client relationship, because we think that they need what we're building in that industrial infrastructure network, and they will help us build an elevator on the moon. So it is very, very symbiotic, and we're very committed to it. With that, Joe Luttrell, let's do ground station, sir.
Okay. I kind of switched things up, but I do want to answer.
Oh, sorry.
Jason.
Yeah, I did. Sorry.
No worries.
Not-
But Jason had a couple of good questions there,
Yeah.
primarily about IR links. What you're seeing is a visible light laser. We use that in the studio just so that we can keep track of things while we're doing the research. But ultimately, we're going to be using a device that works at what's called 1550 nanometers. That's an IR light system. So yes, it is IR. The biggest problem with that particular system is that there are issues if it's raining. If you have extreme cloud cover or it is raining, it's going to interfere with the beam. The solution to that is always have multiple ground stations or pick locations where it doesn't rain a lot. The Mojave Desert comes to mind. We're also looking at the Oklahoma Spaceport for putting a ground station there. There's not a lot that happens in Oklahoma other than tornadoes, and we can deal with that. So hopefully that answers some of those questions. And I'm available if anyone ever wants to ask questions about what I do. Just say the word and I'll talk. I don't do a lot of things that are top secret. The secret sauce I never mention. So, and there's a lot of secret sauce in what I just described. Okay, so the last thing is that, all right, so you've got the ground station, you've got the laser, you need to have a platform for the laser to be on, for the experiments to be on. And that, of course, is our Pocket Cube satellite, which is about this big. But you just don't put this in space. I mean, you need a unit called a deployer in order to make that happen. And so that's what these big boxes back here, I'm going to just turn this slightly so you can see them. Okay, so this one back here, this is a 1U CubeSat deployer. It's the only one of its kind on planet Earth, apparently. There was one other company that made them for a while, and they went out of business. So we're the only company that produces a 1U CubeSat deployer. And all it does is it has an industry standard connector, and this is a control box that simulates what the signals would be on the rocket itself. So when they put the rocket together and they've assigned all of the payloads, they mount this in a specific location for weight balance, and then they run this cable into their system. And then the rocket's pre-programmed. A lot of people don't realize that when a rocket launches, they don't have any control other than to blow it up. Okay, the rocket is doing all of the work. It's already been pre-programmed. It's going to do what it needs to do. That's it. It has many failure modes, but there's no person that can radio up and say, don't do that. Okay, the rocket is going to do its thing. So we're in a pre-programmed location, and then it sends a signal. All right, and so it goes ahead and activates the power at that point. And then when it says, all right, it's time for you to deploy, and out the door we go. So that spring's a little energetic for this particular launch. We're going to go a little slower than that. They don't like people leaving a rocket at faster than 1 meter per second because it throws the rocket. Again, action reaction, right? So if it's thrown out at a very high velocity, it's going to put the rocket off trajectory. And so all of that is calculated. Again, the rocket can't do anything. It's already pre-programmed. It will do its best to compensate. So when you say 1 meter per second, it's got to be 1 meter per second. And so that's what we're going to do.
Beautiful. Let me ask you for 2 more minutes to update us on our satellite. What is going on with RSAT? What's going on with InnoSpace? Where are we?
Okay, well, InnoSpace is still targeting a no earlier than November of this year. The FCC, as I mentioned before, their paperwork can be a long, painful process. The orbital debris assessment is finished and in their hands now. It's just a little bit of, the regulatory needs to be done. As far as the satellite itself, we have a couple of the pieces that, because this material is so strong and I'm afraid that it's going to cut through the 3D printed spindles that it's made out of. We're shifting that over to using stainless steel for those wheels.
That's
They'll
an
be
upgrade
slightly
I hadn't
thinner.
heard before. Okay.
Yeah, the reason why I'm going to go with stainless steel is it's fairly inexpensive to work with. It's known properties. We can cut the thickness in half, so the weight remains the same, or the mass rather remains the same. And it's also going to be done here in America. The objective is to send the final file to a company called Send Cut Send, and they will actually make the product and send it back to us. So shout out to the guys over at Send Cut Send. They do amazing work. And yeah, so they're going to make that particular set of parts just so that the stress doesn't cut into. That's one of the things that you can do all the testing you want, but until you actually start stretching this and you realize, oh, it's kind of like making grooves.
Right.
Not a good idea.
Right.
But that's the material you want. I mean, if it's cutting through my carbon fiber stuff, you want something a little stronger. So that's what we're doing.
Terrific.
Okay.
Terrific. Okay. Jason, Sean is saying to go look at your LinkedIn messages. I don't know what he's sending, but I thumbs upped it for him. And with that, we're going to bring John Connell and I on to talk about some kind of, I'm not going to call them breakthroughs, but maybe I'm going to call them epiphanies, a series of epiphanies where we started looking at L1 from a logistics perspective. I think everybody that knows Sean and I, we have a old and dusty but still relevant logistics background. And we started thinking about L1 from the point of view of, if you really had a giant space station at L1, what does that mean? So, John, I'm going to bring up our website, and I'm telling everybody that it's a website because it's going to be live for y'all to play around with. Except, why can't I find my website? Hold on a second. There we go. So we built this thing. All right, John, you start off. Tell them what this thing is.
Okay, it's looking at the delta V from places in the solar system to other places in the solar system, and in particular, it's looking at journeys from L1 to other places. In doing that, we work out the delta V. There's a bunch of assumptions that we have to make about orbits, and if anyone's interested, we can tell you what that is. But we're flying from L1 and to a place, say Mars, and we're flying from Earth, say, to a place, Mars, and we're comparing the journey times and the fuel you'd need to burn, and it gets really interesting. So obviously, we're looking at establishing a base at L1 with a large car park, trailer park, storage area, and it will be a great place to set off to all other ports.
I'm going to first pull up. I'm going to shrink it down, and let's talk about the moon, right? And what we've got here is a set of destinations if you are moving from L1. And what is the comparison of if you're taken off from the Earth, for example, to L1? Same thing with the Lagrange points. You've got 1, 2, 3, 4, 5. If you want to get to L2, from L1, it is surprisingly low energy, surprisingly low. If you want to pop out and get to L5, same story. If you start from L1, everything is cheaper. We've got a little bit of a description down here about what this is all about, but let's kind of take it from a larger perspective here. If your destination is the moon and you launch from Earth, it's going to take 3 days. But you're going to use 300 times the amount of propellant than if you are going from L1. Now, the reason this is not on our website right now is that we actually do have some typos in here that we are aware of. So it'll be up over the weekend. But we've put some pretty cool stuff in here. If you want to get out to Mars, same story. It is 47 times cheaper energetically to launch from L1 than it is to launch directly from the Earth. We've got rocket comparisons. So, John, where do you want to go with this? You're driving this part of it.
I'm gonna let's go back to what Lagrange actually is. I'll share a few slides and let's talk about the history of it and what's there and what you can and can't do with them, please.
Okay.
So let me go ahead and share something. Just a few fun slides. I hope they're fun. That one. No, not that one.
You're doing a share?
Yeah, but I'm not able to see the screen that I'm trying to share. That's bizarre. 1 second.
In our private chat, Joe Luttrell is reminding everybody the Robert Heinlein quote, get to low Earth orbit and you're halfway to anywhere. And that is true, right? So it's still, no matter what you do, it's still, depending on what you count, 9.3, 9.4 delta V to get to orbit. It ain't easy. It's not easy. But once you get there, you can go anywhere else you want to go. And that's what the magic of L1 is. I got you, John. There you go.
Thank you. Okay, so those are the Lagrange points, which you've all heard about. I actually did a bit of research on Lagrange. They should really, L1, 2, and L3 should be called Euler points because it was Euler, or in England we call him Euler, discovered those points. Lagrange did L4 and L5, but the world knew about the other ones before him. Those guys, it must have been interesting being alive in the Enlightenment. If you look at the work that they did, it kind of defines everything that we do now, and it's why I can't analyze our tether because it's too long by aspect ratio. But they basically wrote everything. And if you go, there's a Wikipedia page on Lagrange. Look at the things that are named after him. It's a wide scope. This guy was just everywhere. He developed the meter, the 1 meter. I didn't know that. 1 meter. That was Lagrange. I find that absolutely amazing. So.
Okay.
I'm trying to change my screen and it won't let me. Damn it. Okay, I think I'm going to have to stop sharing. Start talking, Michael. I'm sorry. I've got.
All right, no worries. I'm going to go back to the. The website that we're building. Oops, not that one. And just kind of talk through some of the pieces of it here. Hold on, I want to see what Dallas is saying. Don't forget to compare apples to apples. Compare Earth to L1 to Mars with Mars. Yep, I'm going to show you exactly that. So Dallas is saying, don't forget to compare apples to apples. Compare Earth to L1 to Mars with Earth to Mars with the moon to L1 to Mars. Yes, absolutely true. I did not do a complete apples to apples because I'm making the assumption that whether you used geese to fly to the moon, and that's an old myth that I said that on purpose. I don't care how you get to L1. I'm counting this is an energy point from L1 out to anywhere else. So yes, you still got to get to L1. That doesn't change. But what we've done is taken a look at, pretty obviously wherever you want to go in the solar system, you just save energy. You don't save a lot of time. As we did this over and over again, we decided it was okay to downplay the time savings. That's as close as we could get to that apples to apples comparison, Dallas. I think this is pretty interesting, though. Getting out to Mars, and again, Dallas, this is a direct flight versus L1. So yes, you definitely still have to move from Earth to L1. You don't ever get to give that up, but I think there's going to be a thriving economy at the L1 station, at LiftPort station, and some of that stuff is going to be built on site that'll never go back to Earth, and that's what we're trying to look at here. I'm not saying that we got any trips going out to Neptune anytime soon, but it's pretty good. It's funny, the farther away that you go, the less it matters whether you come off of Earth or come off of the L1 station, because you're still dealing, the primary source is still the sun if you're going all the way out to Neptune. So 30 years doesn't change. Delta V changes a bit. It's about half, but I don't know that that's as significant as if you are close. And close does matter, right? If you want to get from Earth to the ISS, sure, it doesn't take any time at all, 0 days. Versus if LiftPort's trying to do it, if somebody's trying to do it from L1, it's going to take 5 days. But again, the energy trade-off is there. So I do really want y'all to take a look at this. It will be on the LiftPort website, liftport.com website, probably on Saturday. There are some known problems here. John, do you want to talk about safe havens?
Yeah, can you hear me? My computer's completely locked up, so I can't come out of that share. But if you can hear me, I'll talk about it.
We can hear you loud and clear. Your video is off. I would just go ahead and turn off your video.
Okay.
Yes, and Dallas is completely right. You're trading energy for time. Yes, absolutely.
Yep. So I remember Apollo 13 happening, and it happened on the outward leg from Earth. And the terrible thing about that journey is they had to go all the way around the moon, go around the dark side, and come back again. And fairly obviously, we need a safe haven. If we'd had our L1 port in place, they could have arrived there. And I think it's important to offer safe haven to anyone that's in trouble. And that'll certainly be a service which we would provide. And I'm sure the whole world would add features to. And one of the things we can do with that simulator is simulate a problem at any point between Earth and the moon, and simulate a bailout to get to L1, what your delta V would be, and how long it would take to do it. And that's got to be of great use. And presumably it will have some minor medical treatment and food, air.
Let's have air and thermals, right? Let's have that as a minimum. But it's half the time, right? Earth return is 4 days. Safe haven to L1. Now, again, this is orbital mechanics. It's not like you could just like flip your spacecraft around and go the other direction. So take this with a grain of salt, right? But we are starting to think about what we're able to do with this system. And the other thing to kind of think about is, launching from the surface versus launching from the station, and then comparing how big a rocket you would need. And this, by the way, is the error that we know is in here, which is the graphics don't really work to the math. So it's a thing that isn't finished yet. But this delta V ladder and the rocket compare, and this just to understand what the gravity well really looks like. This is an old picture. People have seen this before, but we're trying to make people aware of like the trade-offs that folks are going to have to.
Another thing that jumps out of me is L2 is permanently hidden from our view. You can never get to it because it's always behind the moon. So that's a great place to put scientific instruments that look out at the universe.
Yep.
Whereas L3 and L1, the Earth is always in view. So it's another great place to put monitoring instruments to you can see half the planet from either side. So that's a great location. We've also done a little bit of work. We know L1 is not a stable location. It's easy to slide off it, and you can station keeping is possible. You can keep in place. It's a lot easier at L4 and L5. Those are equilibrium points. L1, you'll slowly move off it. But we found some orbits where we could, let's say we had a semi we needed to park, but we didn't need it for a month, or there's a line of traffic, you can put circular or halo orbits or Lysander orbits round L1 and L2. They need fuel, but not a lot. And we can bounce between the two of those. So that'd be a great way to create a parking lot that was in flux, but didn't need station keeping at L1, which might block up access to our port.
I'm gonna bring up Dallas's comment again. One of the biggest advantages of L1 versus near rectilinear halo orbit in a NRHO or low lunar orbits, missions can go or leave from the moon at any time. No need to wait for orbital alignments or impose huge margins to leave at any time. We love that. That is certainly one of the things we're going to be talking about in this little simulator that we're building. It's pretty fun. I mean, it is. It's pretty fun to kind of just imagine a future where there's already a bunch of stuff happening at L1 and you just need to start there and go anywhere else in the solar system. I believe, and this is why Connell and Lauren started looking at building this new map. I believe it's a new map of the solar system from that new perspective of L1 being operational. We've got about 15 minutes left. John, did you want to say anything else?
Yeah, I read as I was researching this that O'Neill wanted to put his space stations at L4 and L5, which is nice. And he did an awful lot of work on the math for space, station keeping and illumination and the ton of stuff. So
I got his book.
Me too.
Gosh, normally it is right here. I'm sure this is it. Yeah.
Everyone at Gravitics gets a copy of that. Gets a copy of that book signed by Colin.
Yep. I got two versions of it. One is this space settlements, the design study, and then the actual book. The design study came first, and last year was this is the anniversary of it, I think, to the 50th anniversary. So yeah. So let's go ahead and open this up a bit to questions or comments. If anybody wants to talk, we don't need to run to the full top of the hour. We had a guest who was unable to make it for us tonight, so to join us tonight. So I don't want to hold anybody that doesn't want to be here. But if you got questions, we're willing to be here for the next 15 minutes. What do y'all want to do? Does anybody else have anything they want to bring up on my team?
I just think that the economics for the space, we have a price point that is, when you compare it to other price points from other transportation system, it's extremely competitive. Highly competitive. It's eye-watering competitive, and we have a lot, and we do have leadway with that. So I think that is a very important consideration. And I mean, some people might be on the fence, but the fact that we are bold enough to say we can do that, you might want to pay attention to this. This is something that's got a lot of. It's a game changer, nonetheless. It's a game changer. There's a lot of utility that comes out of this. We not only did we just talk about, a life station, just like out at sea, you have every nation has a duty and responsibility. Same thing. We're up here in space. It's the same risk and stuff like that. And I wrote in the chat or behind the scenes chat. Well, the whole world needs to finance this. So, yeah. I mean, there's a lot of utility. There's a lot more things that you can do from L1. There's a lot more transportation issues that we can help solve by being there at L1. So I do think that this is not a pie in the sky. This is not something this is something that's very much needed.
Well, one of the things that came out of these conversations, again, we've had 2 conversations this week with potential clients that also are interested in becoming potential investors. So two different one. One is a large infrastructure project focused on the moon, and the other one is a downmass space tug company. And both of them have the engineering chops, and they've got the hopefully they have the economic backing. And so, our published price is $5,000 per kilo. That's our published price. But one thing that we're looking at with these client investors, and it's kind of a new category, is if they really are going to be in this ecosystem for the long haul, if they want to invest with us, we will cut their freight rates down. We will lower their freight rates. If they have enough confidence in what we're doing, we will lower their freight rates, so then they get a return on investment in our company, but they also get a secondary return by having lower costs for operations.
Yeah, exactly. And I think I've written about this category because we started to see the picture for the last several months. Is that we're at infrastructure,
right?
But space does not have the financial maturity to be able to finance us accurately. We take what we can get right now because it's the only thing that's available. So, like if a VC comes along with, they're used to doing software. They're using a shorter timeline. They're used to having some. All right, let's see when the revenue starts, and this is when we scale. That's not what happens here. This happens at the back end when everything's built. Mm-hmm. It's like building a toll road. You're not going to make your money until the damn thing's built and people start going through it.
Which is why I was saying I was in the wrong room this weekend. Right?
Yeah, exactly. And VCs might not want to know it, but the truth is they're not the right fit, because you can even look at VCs at C round or companies at C round and D round of fundraising. There's a drop off. a big drop off
Big drop.
because they're stuck because they can't scale because they don't have a viable their product. Even though there's a solution, it hurts. They don't have a customer.
Right.
And so it's really was the first clue. And I saw it clearly whenever I was working on the tier system. When I was developing the tier system, I started mapping financial rounds to the tier system at each level. When I got to between tier 2 and tier 3, which is tier 2 to tier 1, which is from development to scaling, you'll see that drop off precipitous and it's automatic.
Yeah.
And I'm like, oh, that's where the issue is. And that's what it is. And we don't have the right financial tool match. Now we're going to have some people on our other project, Unknown Quantity, that was going to talk about some solutions to that. But
whomever is playing music, can you turn it down or off?
Yeah. So we got solutions. There's solutions that's coming along, but I think this idea right here is what really has some legs. Where the customer client,
right.
I
want to answer Dallas's question. He says, do you have a cost point comparison? So hold that for a second. Price is one thing, cost is entirely different. I believe SpaceX price to the moon is orders of magnitude more than their cost. Yes. Like let's think that through for a second. Their cost might be $1,000, but they're going to be charging their price at $1,000, $5,000, $10,000. We already know that Intuitive Machines is charging $1 million.
$1.2 million from launch to the surface of the moon.
Right. So there definitely is a difference between price and cost. We don't have a good handle on cost. We do not. I'm not going to lie to you and say that we know what this stuff is. To be 100% transparent, I told somebody recently, I thought the idea of talking to a client was 2 years premature. I was very surprised to hear that we have that we've matured to the level of having real conversations with real clients already. I'm very surprised by that. So no, I don't have a good handle on cost versus price. I think I'm in the right ballpark to say that our costs are probably in the $500 a kilo range, and our price is $5,000 a kilo.
Yeah,
those are the numbers that we're operating with internally right now. I'm happy to share that. That's why we're doing these posts, these shows.
And we know how much we can move, and it's really how much money we want to make on moving it.
Right. Our potential client recently asked us to do an iteration of 600 tons a year, which is our current threshold, 50 tons a month, growing it to 6,000 tons a year, 500 tons a month, growing it to 12,000 tons a year. That's 1,000 tons a month. And it was very instructive talking to this client because they're like, well, that's only 10 starships. Think that for a second. That's only 10 starships. So they're already thinking in perspective of that ain't enough. That 12,000 tons a year on the moon is not enough cargo capacity. I don't get told very often I'm not thinking big enough. That's not usually where I live. So it was surprising. Yes, and Dallas, again, that's what we're saying all the time. That is the price once you get to L1. If you figure out telekinesis and can lift cargo with your mind up to the sky, That's one path. More than likely, it's going to be Blue Origin and SpaceX or Rocket Lab or Intuitive Relativity. But our price starts with when you dock at our station, right?
Yeah.
One. All right.
Right.
With that, we got just a few minutes left. I'm going to do round the robin. I want everybody to say thank you and kind of what you think the next month looks like for you. For me, I am focusing on those exact questions that Dallas just asked about price versus cost. We have one of the things that we didn't talk about during the show was that we just created a very detailed budget on what we would do with $500,000. The next detailed budget is $4.5 million, and the next detailed budget is $15 million. Combined, that's $20 million. That is our phase A. So I'll be working on that this month. That's our phase A financing. Phase B is 30 million, and phase C is 300 million, totaling 350 million. That's what we think it's going to cost to build the elevator. I don't have good real numbers for any of that, which is why we're going to spend the time on that 20 million phase A this month. So I hope to be able to share that with everybody next month. Fingers crossed. It's not easy to do that. It's not. So it's gonna be tricky, but that's the plan. Joseph Lauren, you're going to be gone soon. You've only got a couple weeks left. What do your next few weeks look like?
I finish up the simulations, deliverables, individual projects. I finish up what I'm doing right now, maybe help with a few things that are currently ongoing or just need to get finished up before I leave. And then I am off to school again.
Yay. Good. All right, cool. And Dallas, of course, I know you love the elevator idea, and I love that you point out issues that need to be addressed. So keep doing what you're doing, buddy. Thank you so much for all of your support and time. Latrell, what are you doing this next month?
Well, other than the obligatory paperwork and getting all of that in order, we're continuing to develop on the satellite, and we're hoping to bring our big laser centering printer online so we can start building some really cool parts.
Awesome.
That's a whole different methodology than the FDM that we're using, so we can print things in mid-space, and that's a cool thing to do. So that will improve our product immensely.
John Connell, we got 3 minutes left and 2 speakers, so go fast.
I'm going to be supervising Joseph, trying to make sure we can put his name on something patentable, which will be cool for his career. And me, I'm going to be doing more and more simulations. First, to help the company sell, and second, to help the product work.
Outstanding. Thanks a lot. And Alejandro, thanks for your support, buddy. I didn't know you were here, but glad you are. Sean mixed up AM versus PM when he set up the show, and Alejandro was sitting there ready to go at 8 o'clock this morning. So thanks a lot, buddy. Appreciate all of your support for the years. Sean, go ahead. What are you doing this next month?
Well, saying we're operating the Unknown Quantity podcast and publishing the Better Futures Dispatch. I am working on doing a live version of the Better Futures Dispatch at the end of the week. This won't be ready this week. It might be next week when I do it. Just a recap of the week. Go over, and I'm actually going to work on some of the financials for LiftPort, bringing my skills in, and see what we can come up with that makes sense. And I'm finishing up these 2 writing projects about spaceports and the financial side of it, of the space industry.
Awesome. I couldn't do any of this stuff without all of y'all. I'm so grateful to our team. I'm looking at the notes in the chat here. Happy to chat with Jason and Alejandro. Let's do that offline. And I appreciate all of the support that we've gotten from our community. This stuff can't be done without you. So with that, I'm going to sign off. Appreciate all of y'all, and we'll see you next month. I'm pretty sure that the show is going to be on the, dang it, I had it right here. On the 5th of August. I'm pretty sure it's going to be on the 5th of August. So hopefully we get back on track. All right. I will see everybody. Thanks so much, and have a great night, y'all. Appreciate it.